Hi, welcome to my channel, Jabber Time. I'm gonna go over exponential growth and decay. The main formula is y equals a sub 0 e to the power kt. Of course, a sub 0 has to be greater than 0. We're gonna talk about doubling, time, and half-life. I'm gonna save you some time and have notes. As you notice, if you've seen some of my videos, mainly they are lecture videos with notes. So I write the notes before recording to save you some time, and this is what I mean. Let's take a look. If I slow down and write everything as I'm recording, that's gonna take longer. Trying to cover the topic with enough examples in less time, hopefully like 20 minutes max. Let's get started. Modeling exponential growth and decay. This is the way it should look like as a formula. I have them right here, identical. The difference between this and this is down below. This is decreasing when k is negative. So if this k is negative, we are decay mode, in decay mode, and if k is positive, it's going to be increasing, which is exponential growth. They both share a lot, and they are right here, one-to-one function. They pass the horizontal line test, which means they do have inverse functions. Horizontal asymptote is the x-axis, y equals 0. The domain is all real numbers in both cases. The range is from 0, not including 0, up to infinity. X-intercept will be none because they don't touch the x-axis. The x-axis is the horizontal asymptote. If there is no shift right here, as you can see, there is a basic formula without any transformations, right, left, up, or down. It's gonna go through the initial amount. We call it initial amount, a sub 0. So this point is a key point to know. 0, a sub 0 in both cases. To explain more about 1 over k, why they're using it, and negative 1 over k in both cases, as you can see, I'm gonna show you more notes. Here we go. That's the same graphs that we were looking at. This example is exponential growth. This example is about exponential decay. K is negative 2, k is 3. As I said, it's lecture notes, so I'll have all notes for you instead of writing step by step. Take a look. A sub 0 is 2. The initial amount is 2, so the graph is going to go through 0, 2. A sub 0 is 3. The graph is going to go through 0, 3. K equals negative 2, less than 0, decay, decreasing, as you can see. K equals 3, positive, growth, increasing. You could see it right here. Now, when you plug in 1/3, why 1/3? I mean, in algebra or pre-algebra, when we give a straight line like y equals 2x plus 1 to students to graph and give them a table to fill and graph it on a grid, we kind of like substitute 0, 1, 2, 3, 4, 5 for x, or we use them because it's independent. We could use anything. But here, it would be convenient if you want to use some numbers like 1/3, because 1/3 times 3 is 1. You could go 2, but that's going to make it larger to graph. You need a bigger scale. So 1/3 will work with 3 and will simplify. Take a look. 1/3 times 3 is 1. E to the power 1 is e. Times 2, 2e. So the answer is 2e. That's right here. So imagine if you want to plug in, let's say 2. That's going to be e to the 6 times 2, which is going to be harder to graph. You need a bigger or a scale that takes you all the way up to the value of 2e. Why negative 1/3? Because negative 1/3, same idea like 1/3, but with negative, will simplify to the with the exponent 3, and we'll make it negative 1. E to the power negative 1, we could bring it down to the denominator and call it 2 over e instead of 2 times e. Same thing applies here. Okay, I'm not gonna read all these numbers, but you could see the similarity in plugging in. Here I'm gonna plug in half because it works nicely with the negative 2 and negative half. You could try it and we'll see that this one will take it down. When you apply negative and you already have a negative, it's gonna change it to positive. So when you are on the negative side, it's gonna end up with positive, which is a big number. That's why it goes up on the left. Okay, I think that's good enough for this slide. Let's move on. If you need a bigger picture about what's going on so you could see exactly the details, you could go through this and take some notes. One thing about watching YouTube videos, if you want to slow down, because some slides I do have a lot of notes in it, you could slow down by hitting the space bar. The space bar acts like play and pause like a remote control. So let's move on. As I said, like, I'm not going to go through this. I just want to show it to you in a bigger picture. Because it's notes, I want to save you some time and go through written notes, as you could see, and move on. Here we go. A population of bacteria doubles every hour. The keyword is double, and every hour is another keyword or information, piece of information that we have. If the culture started with 10 bacteria, that's my initial amount, graph the population as a function of time. This is a graph. Notice that we did not graph anything on the left because we started, when we started with 10. This is 10. Kind of hard to see it, but I'm just referring to the 10 as my initial amount, which is a sub 0. So a sub 0 is 10. That goes right there, and that shows on the graph. To find k, the rate, we use the fact that after 1 hour, every hour, the amount doubles. So 10 becomes what? Becomes 20. 10 initial, 20 as an output in 1 hour. T, instead of T, I'm using 1 hour. All this information, they correspond. 10 initial, after 1 hour, my output is 20. Divide by 10, divide by 10. I get 2 equals e to the k. Apply it into both sides. Bring the k up front. So I have ln 2 equals k ln e, but ln e is 1. Think about it in a different way. E to the power what equals e? It's e to the power 1. That has to be 1. So ln t equals 2. Ln 2 equals k. Or differently, if you want to write it the other way around, k equals ln 2. Now this is for this example because it's every hour. Later on, we're going to do it in a few minutes in general, not like every hour. So it's going to be k equals ln 2 over t. If you are using double or half-life enough examples, you'll notice that those formulas could be used, could be useful if you have them on the side, because it's going to end up the same process. Just like an idea or hint for you. Here's the formula. We agreed that this is 10, my initial amount. Instead of k, I'm writing ln 2. I could rewrite this differently without base e. This is something that we need also to practice and be aware of. Take a look. One way to do it is, since this is like ln 2 times t, it's like a times b. But we have a formula that says a to the power m times n comes from a to the power m to the power n. So I do have this right there, m and n, comparing it to here. I want to rewrite it this way, and that's what I did. I took this all the way up as n. Why is that? Simple reason. Look inside. An exponential with base e and logarithm with base e, ln, natural log, they're inverse of each other, they cancel. And that's what you have left, 2. E to the power ln 2 is just 2, because ln and e cancels. And that's it. That's the other answer. This is correct, but they are different forms. That's with base e, that's with base 2. That's like doubling. If you notice that, that's 2, initial amount is 10, and times 2 to the first, times 2 to the second, times 2 to the third. So every hour it doubles, and that should do it. Let's talk about half-life. One of the common terms associated with the exponential decay is called half-life, like caffeine and so on. When we take vitamins or medicine doesn't stay in the system forever, and it doesn't decrease as an amount linearly. It decreases exponentially as a decay function. So half-life is one concept that is useful. The length of time it takes an exponentially decaying function quantity to decrease to half its original amount. So if you start with 50 and after, let's say, 2 hours it becomes 25, that means it went half the amount. The half-life is 2 hours. It's how long it takes the amount to go down to half the original quantity. That's the meaning of half-life. To find the half-life of a function describing exponential decay, we solve the following equation. We're gonna consider that the initial amount is a sub 0, but the output is half of that. Here we go. You see that? That's called half-life concept. We start with 20, this becomes 10. We start with 50, this becomes 25. We're going to solve for t. That's in general. So divide by a sub 0, both sides. These are always the same whenever you talk about half-life, even with numbers 20 and 10, 25 and 50 and so on. So I end up with half on the left, which is always the case, as I said, e to the power kt. We're gonna apply ln to both sides to bring this up front, just like the last video, which is going to be linked down below and at the end of the video. So we have ln half equals ln e to the power kt. We could do this as ln 0.5 and keep it, or we could apply ln the quotient or the quotient rule for logs, ln 1 minus ln 2. On the right side, kt is going to go up front. We're going to bring it up front. When you bring it up front, it's going to be kt times ln e, which is ln e is 1. But ln 1 is 0. The graph of ln goes through 1, 0 on the x-axis. Because it doesn't have any shifts, right or left or up or down, it goes through 1, 0. 1 for x and 0 as an output. That's my input. E to the power what equals 1? E to the power 0. So the answer is 0. That's why you don't see it right here. Ln 1 is 0, and this right here is bringing kt up front, or cancel ln and e, you get kt by itself. Alright, we're almost done. To solve for t, I'm going to divide both sides by k, and I end up with this. Or differently, if you want k by itself, you switch them and solve for k and divide by t. Either way. Since t, the time is positive, k must be, as expected, be negative. Let's take a look. This is what we expect if you solve for k. This is in general. Earlier in one of the examples, we had k equals, I believe, something like ln 2 or minus ln 2. Without the t shown, because t was 1 every hour. And let's see. If you want to solve for k, t is positive. That's what I'm writing right here. Ln 2 is positive. T is positive, time. Divide them and apply negative. It's going to end up negative. To support that, yes, it's going to end up decay. Means the k value has to be negative, less than 0. Okay, more notes. Finding a function, the function that describes radioactive decay. Same idea, like half-life. The half-life of a carbon-14 is 5730 years. It takes that long to go half the amount, to become half of it. Express the amount of carbon-14 remaining as a function of time t. Okay, let's take a look. Here's the equation. A sub 0 half A sub 0 divide, same thing. We have k times t, and that is my half-life. If I use A sub 0 and half A sub 0, that means I'm using the time it takes the amount to be half. All they go in the same equation. Solving for k, that's not too hard. We got rid of A sub 0. We're going to apply ln to both sides. We're going to bring this up front. We're going to divide by this number to leave k alone. And now this is my formula. Express the amount of carbon-14 remaining as a function of time. Just write the formula with everything in it. So that's the formula that we have. Notice that k, if you evaluate this using a calculator, it shows that it's a negative, less than 0. So just to confirm, because if you end up with positive, something is wrong. Okay. As you notice, I'm writing notes, and with this kind of math, I don't want to just be writing as I go. It's like you write kind of like lengthy notes, which is not practical, unless if I want to make a video for an example or two, but also that's not enough. So, doubling time. The time it takes for a quantity to double is called the doubling time. We saw an example, but there is more. This is a formula one more time. We're going to call A sub 0 became as an output to A sub 0. We're going to divide by A sub 0. We're going to end up with 2 on the left. Same process. To solve, I'm going to apply ln to both sides. We're going to bring kt to the front and cancel ln and e and write on the right side just kt. Solve for t, divide by k, or you could solve for k and divide by t, either way. So doubling is always the same. T equals ln 2 over k, or k equals ln 2 over t. If doubling time is 1, this is going to end up ln 2 by itself. This is another application. Newton's law of cooling. The temperature of an object T in surrounding air with temperature T sub S will behave according to the formula T of T equals A times e to the power kt plus T sub S, where T is the time, this right here, A is the difference between the initial temperature of the object and the surroundings, that's this A right here, K is the constant, the continuous rate of cooling of the object. Here's a problem that I'm going to go over it and save you some time by having the notes ready. Let me show you what do I mean. That's short notes for this problem, that same problem. If you need more details, I could leave this for you. You could pause the video by hitting the spacebar and go through the steps. But I want to save you some time and discuss the problem and the major steps in it. So here we go. A cheesecake is taken out of the oven with an ideal internal temperature of 165 degrees Fahrenheit and is placed into a 35 degrees Fahrenheit refrigerator, which kind of hard to imagine. First time I was looking at this problem, I go like, you're taking a cheesecake from the oven straight to the refrigerator? I wouldn't do that, but that's what the problem is. I think you get my point, right? After 10 minutes, the cheesecake has cooled to 150 degrees. If we must wait until the cheesecake has cooled to 70 degrees before we eat it, how long will it take? Let's get started. Now, earlier we talked about A. We're going to start with 35 as the surrounding refrigerator temperature. That's called the surrounding temperature. And we have a 165 as initial temperature. The cheesecake is at 165 temperature when we started. That's kind of like the temperature that we have. The surrounding temperature that we're putting it in is 35. And I guess by doing the definition right here, A is the difference between the initial temperature, which is 165, of the object and the surrounding. The surrounding is the refrigerator, which is 35. 165 minus 130 minus 35 is 150. Sorry, 130. Too many numbers. So it's 130. And if you want to take your time, 0 for t, because we are starting, we're counting t as 0. We have 165, that's the first reading. Plug them in, e to the power k0, which is e to the 0, which is 1. 35 is my surrounding t sub s. And 165 is our reading when we started with t equals 0. Do the math, it's 130. Okay, that is the surrounding, and that's A, which is the difference between 35 and 165, as the definition says, or you could do the math and do it yourself. Now, we have 35 here, we have 130 here, we don't know K. K, which is defined as the constant, the continuous rate of cooling. How do you find it? Well, we have another point. It says after 10 minutes, cooled to 150 in 10 minutes. So I'm going to use 10, 150. We'll put 10 for T and 150 for the temperature at that time. I skipped the steps. If you want the steps, they're coming in the second slide. You end up with k equals negative, which supports that it's a decay exponential function. Negative 0.0123. Put it where it belongs in the formula. And now, to answer the question, it says how long it will take to reach 70 degrees. 7 degrees is my output. We're solving for t with the steps being skipped right here. T is about 106.68 minutes, over an hour. Need more steps? They're all right here. It's about 1 hour and 47 minutes for it to cool down to 70 degrees. That's if you put it in the refrigerator or taking it from the oven, which, as I said, I won't do that. Okay, let's move on. I'm not gonna read this. I just called my videos. Most of them are lecture videos with examples. And I do take the time to write the notes and the steps to save you the time. I don't want to end up with a video that is 45 minutes or 55 minutes. Who's gonna watch a lecture video of 55 minutes? I do my best to make it around 20. If I could make it less, yes, sometimes it's hard, But after I finish my lecture videos, I'll go back and add more examples, example here and example there with the same topics. So started my YouTube video like a year ago, and I'm thinking about years from now, it's gonna have a way more than 150 to 60 videos, which I have at this moment. Let's move on. Choose an appropriate model for the data. Well, you have a table right here, and they are saying, is this linear or exponential or logarithmic model? I'm circling 1, 0 because the focus with me as I go, I want you to stay focused with me on 1, 0. That's a key point. I picked another point. I don't want to pick a point next to it. There is no need. You could do whatever you want. But I picked the last point. Now, why 1, 0 is a key point? Let me show you. If you take your time to the best that you can by hand or using a graphing calculator, put the numbers in a table and graph it, this is what I have. First, we plot the data on a graph. Well, I could see clearly here it's not linear, so this is out. To me, it's not exponential. Why? Exponential either grows up or goes down, decay. Decaying or growing. Both ways, it's concave up. Logarithmic functions are concave down. So my assumption, this is logarithmic. Because it's going through 1, 0, it's logarithmic that is not shifted right, left, or up or down. So we're gonna reject linear. We're not gonna take it exponential because it's not concave up. And we're gonna use a simple graph or formula, which is a times len. You could use log, of course. Len bx. There is nothing next to x as like bx minus c, because there is no shift right or left. And outside, I'm not writing like plus d because the graph is not going up or down, just because it's going through 1, 0. If it's not going through 1, 0, I might consider more detail, like, plus c and outside plus d and so on. But we need more information and more points to use. Anyway, let's stick to this form. No transformations. Plugging in the point 1, 0, that's my key point. I get the following, 0 for the output. And instead of x right here, instead of x, I'm going to write 1. There is no need to write 1 times b. Well, if I have a product of two things equal 0, that means with the principle of zero products, either a is 0 or len b is 0. But a cannot be equal to 0. Because imagine if a is 0. You don't have even a len or a natural log in your way. All the time, y is going to end up 0. So a cannot be equal to 0. Well, if len b equals 0, use mental math. E to the power 0, because the base is e. E to the power 0 is 1. And that's what's going to end up equal to the argument b. So b is 1. Okay, let's go back to the problem. And instead of writing a len b times x, we're going to write a len 1 times x, which we're going to have to write down. Okay, now we're down with the letter a. We had a and b, now it's only a. How to find a? I'm going to use another point, like this point. So let's plug it in. 9 for x and 4.394 for the output, as you could see. Solving for a, divide both sides by len 9. Use a calculator, it's approximate to 2. Go back to the formula and put it in approximate to 2 len x. Now let's support that graphically. Well, because it's natural log, the restricted domain is x greater than 0. We know this. If you want to graph it on the same grid, you're going to have this, which supports our data. So that's another way to support that, yes, we are applying this formula that deals with these points. Not only the first point, 1, 0, and the last one, all of them, it goes through them. Now, if you want to go more, you could take 2n as a power rule in log. Becomes ln x to the second. If you do that, you could see the graph. It's the same thing. You could graph this. But if you don't pay attention to the restricted domain, which is x greater than 0, because here you could plug in negatives. But should you do that or not? That's a different question. Because negative 5 squared becomes 25. So yes, you could deal with negative 5. Where earlier here you can't. Ln negative 5 is undefined. So if you want to include negatives, your graph is not going to be on the right side, it's going to be right and left. Just something to keep in mind. My last problem. This is an important one, and it has only one piece of information that is critical and important. Here we go. How do you change exponential equations with base 3.1? It's like you're starting with 2.5 and you're not doubling. It's a little bit more than tripling every time. 3.1 to the power 1, 3.1 to the power 2 every hour, let's say if it's every hour, to another form with base e. How we could do this? So simple. That's what we're given. Take a look at this. This is simple and not really hard at all. Take a look. You could rewrite it this way. If you want to go back to verify, look, e to the power ln, that's exponential with base e, and ln is the log, the natural log with base e. They're inverse of each other. If you cancel them, you go back here. So you could call it a trick, you could call it skills, but that's a good way to do it. We're inserting exponential, base e, and its inverse, which is natural log. Now, I'm going to use the power rule in log and bring x up front right there of ln. Here we go. Imagine if this is a number 5, like a 5. I don't need to calculate it now, but I just want to tell you that it's like a number. Instead of writing x times 5 as an exponent, we could write 5 times x, like rearrange. And we're done. Y equals 2.5 e to the power kx or kt. That's what we have. We started with this format. We ended up with this format with base e instead of base 3.1. And the key is right there. That's how we should do it. And I think it's good enough for this video. Thank you, and I'll see you in the next one. Take care. Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.